Greetings. My name is Debendra Sharma. It's an honor to deliver this keynote at the Open Fabrics Alliance virtual workshop. Today I will talk about how Universal Chiplet Interconnect Express UCIe will result in innovations at the package level. I expect UCIe will result in heterogeneous composable systems at the package level the same way PCI Express and CXL have resulted in building composable systems at the board level. Here is the agenda for today. We'll start with some of the mega trends in the compute landscape. Then we'll talk a little bit about interconnects and fabrics as an important pillar of compute. Then we'll start talking about on-package interconnects. What are the opportunities and challenges? And then we're going to dive deeper into the Universal Chiplet Interconnect Express, UCIe, which is an open standard for chiplets, and then talk about some future possible directions. Now let's take a look at the mega trends in the compute landscape today. What we see is a virtuous cycle of growth as we get more and more devices. There is more connectivity. There are more usage models evolving. There are more applications coming through. There is more compute in the cloud and data center. And we are generating a lot of data. We're deploying AI to process those data. There is needs in the automotive segment, cloud segment, enterprise servers, PC, mobile IoT, storage, all of those. Each of them has insatiable demand for compute, storage, data movement. And what's happening is that we are getting more and more innovative applications that are leading to even more data, which is in turn is turning into more and more innovations. And that's how that whole virtuous cycle of growth is continuing. And in this process, the interconnect is an important pillar of compute, along with the compute itself, storage, memory, and software, process technology, security. These are all very important aspects. And today's talk is on one aspect of the interconnect. Now, data generation and processing is exploding, as this IDC graph here shows, and you have the usual suspects: cloud, 5G, sensors, automotive, IoT. These applications are demanding very aggressive time to gain insights in real time in these large data sets. So net is that we have to move the data faster, store more data, and process all that data quickly, seamlessly, efficiently, and most importantly, securely, and also determine where in the storage hierarchy we need to store that data. In each of these aspects, interconnects play a critical role in the compute continuum. This is the slide that I had talked about in my earlier keynote 2 years back, where this is the view or the vision of how the data center should evolve. Pretty much there are different components to this, right? Things need to be seamless, whether we go from the cloud to the edge or edge to the cloud. Things need to be predictable and secure. Services needs to be anywhere, and optimize total cost of ownership, taking into account hardware and software. And it migrates down at the hyperscale level, to the rack level, to the server level, to the chip level. They all need to play a part in realizing this vision. And the vision is there in response to the challenges of the data explosion that we talked about. Now let's talk about how interconnects and fabrics play a critical role in this changing compute landscape. Now let me talk a little bit about the taxonomy of the different node level interconnects and identify some of their key characteristics and differences. I would broadly categorize the wired interconnect world into two categories: those that are latency tolerant and those that are latency sensitive. And fundamental reason stems from the scale they are deployed, resulting in some key differences in their characteristics. So networking interconnect, this is what we use today to connect from at the rack level, at the pod level, at the data center level. And pretty much every server has some networking interconnect that comes out, be it Ethernet, InfiniBand, or any other networking interconnect of choice. These interconnects, they need to scale to hundreds of thousands of nodes at the data center level. So they are narrow. They generally lead the speed transition, often at the expense of latency and cost. And that's where The key there is to deliver more bandwidth within a fixed set of wires. Now, in contrast, the broad class of the other types of interconnect, which I'm going to call as load store IO interconnect, because they have architectural ordering semantics with memory load store semantics. These are both latency and cost sensitive. And examples are things like PCI Express, Compute Express Link, CPU to CPU symmetric multiprocessing coherency interconnect, such as Intel's UltraPath interconnect or any memory interconnect. And because of that direct memory access semantics, they tend to be uber latency sensitive. Even a nanosecond impact to latency for memory or coherent access may have noticeable performance impact for some applications. And we have provided some of the PHY latency numbers from pin to pipe, which is an industry standard interface over here, less than 10 nanosecond. And those haven't really changed over the last few decades and few generations of evolution of these interconnects. Now, so that's the part where there is the latency sensitivity, but because we also have hundreds of lanes, we also are very much sensitive to the power because they are, every CPU socket has hundreds of these lanes coming out. Cost is important. Silicon area is important. We need to be backward compatible. We talked about latency being important, and these are typically on board. And we are gradually moving from there to cables and backplanes and covering the rack and beyond that I had talked about in the keynote a couple of years back with CXL. Now, there is the other class of interconnects that's gradually evolving that we're going to talk about more is at the package level. And this is where we will focus today. We'll talk about Universal Chiplet Interconnect Express, which is a standard for on-package connectivity. Now, the view is that both the on-package and off-package interconnects, they form a continuum as shown here that needs to work seamlessly. And Intel led the standardization of the on-package interconnects through UCIe Consortium formation in March of last year. Intel also donated the initial 1.0 specification, just like we did with CXL. UCIe meets the needs of the on-package interconnects across this entire compute continuum. It offers unprecedented bandwidth density, as it should, because we are putting things on a package. And this bandwidth density is several orders of magnitude better than off-package interconnects. And we're going to go into this in a lot more detail. It offers an order of magnitude lower power consumption that is proportionate to bandwidth usage, and an order of magnitude lower latency while running all of these as load store kind of interconnects. And that's needed because the scale is thousands of lanes. So clearly things that were there with hundreds of lanes gets multiplied many-fold once you get into this on-package interconnects. But the key idea is that we need to be able to move through these interconnects as a continuum, and load store IO is basically fundamentally with UCIe has moved from at the die level. Of course, we have load store. We are going to the package level, then we are going to the node level with PCIe CXL and all of those, and even to the rack and pod level. And UCIe in this process is really poised to change the compute landscape for decades to come. Now, the picture on the top here shows the system level view with PCI Express only, and the bottom picture here shows the system level view with CXL. PCI Express is 2 decades old. It's ubiquitous across the whole compute continuum. It has evolved through 6 generations, now going to the 7th generation with double bandwidth every generation while maintaining full backward compatibility. PCI SIG has 950 member companies, about roughly. CXL keeps the best of PCI Express, but enables devices to cache the system memory and to map the device attached memory into the system coherency space. So small increments, but with profound consequences on top of PCI Express. Now, the CXL, we enable this heterogeneous computing, we enable disaggregation. Further, CXL enables memory bandwidth and capacity expansion, supporting memory tiering across different memory types to get around the the memory wall. CXL is also an open industry consortium with about 250 member companies. And both CXL and PCI are very successful industry standard due to few important characteristics. They're multi-generational, they're backward compatible, there is a huge ecosystem, there is wide availability of IP tools, there is compliance program that results in plug and play. It's my strong belief that on-package interconnect such as UCIe, which is a standard, it should leverage, and it does leverage, that PCI Express CXL software model, leverages PCI Express CXL protocol infrastructure where appropriate, effectively offering an open innovation slot same way as we have done at the board level. We also need to seamlessly move functionality from the node level to the package level to the die level, as we see in the next slide. Now we need to think about the same software, the same IP, the same subsystem being applied from the node level here to the package level here to the chiplet level over here. And this enables us to build scalable solution. And even though we saw the movement in one direction here, there is increasingly, as we will see later, there is movement from, instead of creating large dies, to do more and more chiplets and with an on-package integration. Now, these kind of effectively the seamlessness of the movement of different IP blocks, these will help us enable build scalable solution. This will offer us economies of scale, time to market advantage, and most importantly, a seamless user experience. Now, for example, we can see a world where you have today multi-socket server systems connected with its own memory, connected with accelerator, networking infrastructure on the board, like you see here. Now, it makes sense in a lot of cases to move some of those functionality into the package as chiplets, because now you can offer better latency, even more bandwidth, and with even low power. And in that case, it makes sense to integrate them into chiplet, as we will see in subsequent parts of the talk. And also, by the same token, somebody might want to pull in some of the acceleration function into the chiplet, into one of the chiplet, depending on the market segment in which they are there. But bottom line is that as long as we keep this movement and we have the same kind of IP infrastructure and all of those things, we can seamlessly deploy solutions from the SoC level to the package level to the node level, which will result in much better user experience. And fundamental idea is that innovations that we have enabled at the slot level today, we need to be able to offer that at the package level, which UCIe offers, as you are going to see very shortly in the next few slides. Now let's look into on-package interconnects. What are the opportunities? What are the challenges? And we start with a quote here from Gordon Moore, who recently passed away, one of the visionaries of our time here. And he's very well known for Moore's law, in his 1965 seminal paper, which basically said that number of transistors are going to double every 2 years. And in that same paper, he had predicted the day of reckoning, where he said that it may prove to be more economical to build large systems out of smaller functions, which are separately packaged and interconnected. And we are already in that world. If you look into mainstream CPUs, whether it is my company Intel's client CPUs, server CPUs, or even if you look into our competitor CPUs, or if you look into the GPUs that are being built there, you have a lot of chiplets that are connected together on a package, and these are already mainstream, right? So chiplets being interconnected on a package has become mainstream, and some of the drivers for this today is effectively we are all up against, as we saw, the demand for computing and everything else is insatiable. And as we move towards the more advanced process node, what we see is that, yes, while that offers us the benefit of tighter integration, we are up against yield challenges beyond a certain limit. And we're also, even if we didn't have the yield challenges, and this is across the board, right? Not just for any one company. We are up against the reticle limit. The amount of processing we need cannot fit within a die. So in order to deliver scalable performance, we pretty much have the same kind of functionality, similar dies on package. And this is what I call scale-up solution, right? So effectively, this is like constructing a 2-socket, 4-socket kind of system except they look like a single socket from a performance point of view, and you put multiple dies on the same package and connect them together. These are today done by everybody using their own proprietary mechanism. So that's the scale up thing, and that's pretty much what is very common today. Now, the other thing that we have seen is this picture here on the right that you see. It was a study done, and it shows that the design costs at the leading edge process nodes are increasing exponentially. So what this says is that even if you did not do any other innovation on a given IP, just to go through that whole motion costs you more and more and more. And then the question is that, okay, for every generation of chip or SoC that we are doing, does everything need to move to the new process technology, or can some set of functionality that is not really changing be put in the older process node and just be reused till we need to make significant changes there, right? And so it's a cost cost kind of a consideration. So that's the other part of the picture which is driving these on-package chiplets. So disaggregation of the dies based on different functionality across different nodes. That's the second motivation here for doing on-package chiplets. Late binding, time to market advantage, right? So let's say if only my compute functionality is changing, but the rest of it is the same. Well, if I just keep the compute as a separate chiplet, I can just replace those chiplets and I get a very fast time to market advantage because the rest of the SoC has been validated. Custom silicon for different customers. So these are the bespoke solutions. So different customers might have different acceleration needs. Even the same customer might have different acceleration needs for different segments. So doing some kind of a on-package chiplet integration, assuming your latencies are lower and all of those other characteristics that I talked about, it might make sense to offer that flexibility of bespoke solutions, these are all real things, right? Then the last but not the least, anyway, this is something that we all know, that different process nodes do different functionality differently, right? Memory is in a different process node, analog, you can optimize better with different process nodes. Co-packaged optics wants to be in a different process node. Logic probably wants to be in a different process node. So these kind of chiplets allows us to effectively deploy the best process node in the most cost-effective way for the best usage that we want, right? So these are the drivers for the on-package chiplets. And then the question is around, okay, so if we want to drive an interoperable chiplet-based ecosystem, what's the best way of going about it? And these are based on, several of us have a lot of experience driving the industry for very successful standards like PCI Express, CXL, from the beginning, right? And USB. Personally, I've been with PCI Express and CXL from the beginnings. A lot of people involved here were with USB also. So this is a distillation of some of those best known practices, and there are 4 components to it, right? And you can split them into 5, but this is just a representation, which is the die-to-die IO, which is the physical layer, and this gets a lot of attention, right? And that's fine. That's one of the components, right? So there you're dealing with, hey, how is the channel? What is the length? What are the bump arrangements? What are the electrical, voltage levels? All of those things, right? Bit error rate. These are all extremely important aspects. So that's one. Second one is the protocols, right? What protocols are running? So if I just get the file layer as a specification, then that's like giving somebody just the SerDes, right? And it's useful, but you just don't know what to do beyond that. But you need to know what protocols to run, and do you need to do something that results in reliable delivery of the packets? All of those are at the protocol level. Then you got the SoC construction level, which is that how do you do this reset of this SoC? How do you do the initialization? What's the security model? And then of course the form factor, right? All of those things. All of these are extremely important in order to ensure an interoperable chiplet-based ecosystem. Now let's switch gears and talk about UCIe, which is an open standard for the chiplets. So the vision for UCIe is on the left-hand side, right? So if you want to think about it, it's the same picture that I had shown where you have some set of computing cores. Those will be in one or more chiplets. You've got some amount of customer IP, customized chiplets, acceleration, whatever you write, NIC, all of those things will be there on the same package. You want to have some amount of memory connected there. And these are all based on UCIe to interconnect them. And ideally, we want to get a 20x IO performance benefit at 1/20th of the power. And we'll go through some of the numbers. But what we want to be able to do is that at this level, these things should be all plug and play. In other words, if I need some accelerator from somebody, I can bring them in and connect it and it will work, right? And I can have 3 accelerators or whatever. I can have 4 accelerators. We should be able to construct the SoC just like we are able to construct things at the board level today. So what are the things that this solves? First problem is, of course, the problem that is imminent, which is that people are up against the radical limit, and they need to against the yield challenges. So the scale up kind of solution that everybody is doing today, well, this is the same model as PCI Express at the board level, where you run your own proprietary coherency protocol, but you can run on the PCIe PHY. So same way, you can run whatever protocol you want to run, but on the UCIe PHY at the package level. So we will enable the SoC construction for those kind of scale-up applications. Now, in addition to that, if it is a true plug-and-play kind of solution, you will also reduce the time to solution. You can enable, you can have lower portfolio cost. You can deploy optimal process technology for the right set of things. Smaller dies always yield better, so that also helps with the cost. It will help reduce the IP porting cost, the picture that I had showed earlier. And overall, it lowers the product SKU cost, because just because you are doing a different SKU with slightly different characteristics doesn't mean that you are doing another tip out of a chip. You are potentially reconstructing on the same package using different mix of the individual chiplets. And the capability also enables us to offer these bespoke solutions, and it scales innovation. All right, you don't have to worry about certain IPs are locked with certain manufacturing process. Doesn't make sense for us to port them over. So it helps us drive the innovation without being bounded by things that are not necessary to be bound by. So the goal of UCIe is to align the industry around an open platform to enable this kind of chiplet-based solutions. And you will see that we're pretty much, it has been so far things are going extremely well from that perspective. Now the other things that we look at, again, this is based on our experience with the driving successful industry standards, PCI Express, CXL, etc. is there are 2 broad umbrellas that basically decide whether a standard becomes widely deployed or not. On one side, you have what I call the key performance indicators. So these are your quantitative stuff, and the other one are some of the other factors which are qualitative, and we'll go through them in some detail. So in the KPIs or key performance indicators, of course, given that this is on package interconnect, bandwidth density is going to be critical. In other words, chiplets will be of a certain size. You need to make sure that you deliver the bandwidth, whether it is linear or area kind of density, you deliver high bandwidth, so that bandwidth is not a constraint in terms of breaking functionality. Energy efficiency is going to be important because, again, you're having a lot of functionality within the today's monolithic die. If you're splitting them up, you're going to have energy consumption bits whenever they transfer over the wires. They cost energy, so we want to make sure that the energy efficiency is extremely good, not just the peak energy efficiency as you have in picojoule per bit, but also we want to deliver a scalable power consumption depending on the bandwidth consumption. And by that, what I mean is, if I consume 25% of the bandwidth, I should consume 25% of the peak power. That's the ideal. And in order to enable that, we need to have very low entry and exit time in terms of getting to the low power state, and also save power while we are there. Latency is important, channel reach is important, reliability and availability is important, and cost is important, right? So we offer standard and advanced packaging options there. On the other side, you want to have factors that deploy all of those things is that you need to make sure that things are going to be interoperable, backwards compatible. You defined a full stack, plug and play with existing software. You want to make sure that the specification is going to cater to different usages and segments in order to be ubiquitous. Otherwise, it becomes a niche. Not that there is anything wrong with a niche, but our goal was to define UCIe to be applicable across the broad compute continuum, portable across different process technology nodes. So there are going to be a bunch of those challenges around debug, repair, all of those things. We take care of that. And most importantly, you need to have broad industry support and an open ecosystem. You can have everything else, but if you don't have the broad industry support, it's just not going to take off. So we did architect UCIe to have the best KPIs, and also we are very mindful, as you will see, of these factors that affect the wide adoption. A little bit about UCIe 1.0 specification. It's a layered approach, and we'll see some of the industry-leading KPIs. So we have physical layer here. We have a die-to-die adapter here. And then on top of that is the different protocol layer support, as well as something called raw mode, and I'll get to them in a minute. And the scope of the UCIe specification is from, it doesn't define the individual protocols, but it's from the just below the protocol layer all the way up to the bumps and or micro bumps, whatever the case may be. So the physical layer defines the, how the link works, what frequency, what's the analog front end, what voltage level, clocking, sideband, channel description, things like link training, lane repair, lane reversal, scrambling, descrambling, all of those things. And of course, we define configuration registers across each and every one of the layers so that there is a software mechanism for discovery. We also define the bump placement and all of that in the UCIe spec. And the physical layer connecting to the die-to-die adapter is through a raw die-to-die interface. We also define that. So again, the goal there is you can buy the physical layer from an IP vendor. You can buy the die-to-die adapter from a potentially different IP vendor, or you can do it yourself, and you can still make all of them work. That's how the internal interfaces are defined. Die-to-die adapter is responsible for reliable delivery of protocols. It has things like also multi-protocol support, so arbitration, multiplexing, CRC retry, all of those things are there in the die-to-die adapter. And on top of that, we have protocol layer, which is, so today, what we have done is 3 broad sets of protocols we have defined, PCI Express and CXL. We also have something called streaming protocol, and streaming protocol can be used for any of the other protocols, like symmetric coherency protocol, for example, for scale-up solutions. ARM ecosystem has AXI, CHI, those kind of things. Memory protocols, all of those things can be mapped through streaming protocols. They take advantage of the whole infrastructure here, just like PCIe and CXL. And we did the bit mapping of PCIe CXL with respect to these FLITs. PCIe and CXL are there for pretty much the volume attach and plug and play. So a lot of your SoC construction issues can be addressed. IO attach is through PCIe CXL.io, memory through CXL.mem, and accelerator using CXL.io, CXL.mem, and CXL.caching semantics as applicable. We also have defined something called a raw mode. So this is, if you do the raw mode, it's just a bit stream. You can, in that case, you bypass the die-to-die adapter, you connect directly to the physical layer. An example would be if I have an SoC, but I have, let's say, 224 gig SerDes in a different process technology. I just put that SerDes, I connect to my SoC. That particular 224 gig, whatever fabric is protocol is running on top of that has its own replay and everything else. So just take advantage of that. You're just using UCIe as a transport between your SoC, which might be in a different process node than the SerDes that you're buying from somebody. In general, so we have a very well-defined specification, keeping interoperability and future evolution in mind. I talked about config register for discovery and runtime operation, form factor management. We have a compliance program, interoperability program. So all of those things are there. So we support both standard and advanced packages. So standard packages is for cost effective, for longer distance. So two dies can be connected using a standard package substrate. So these are bumps between 100 to 130 micron spacing. We also have advanced packaging, which is a little bit more expensive, but it is very power efficient and very high bandwidth density. And we'll see some of those numbers. So there are three examples that we have given here. One of them, the first one is EMIB from Intel. The second one is CoWoS from TSMC. And then the third one is Focus from ASE. And there are many more examples, but you will see that, these things are built with, your dies can be manufactured anywhere in any, any foundry. They can be assembled at any OSAT, and you can mix 2D, 2.5D, and they will still work. So again, picture the things that we've been doing at a board level, we are doing right now at the package level. So we have defined the bump out here for interoperability in mind. So you'll see here that normally the question we get is, hey, aren't we dependent, especially for advanced packaging, on the exact bump pitch? And the answer is no, there is a way of constructing it. And what we have defined is, we have defined a fixed beachfront. So for example, here you got 55 micron to 55 micron on this picture over here. It's a straight connection. Even if it is 40 micron, your Y reduces, your X is the same. So it is again the same connection. So what has happened is that the Y just compresses because you went for a tighter bump pitch. But connectivity wise, you're still going to interoperate. So that's basically how we go through all of these. I'm not going to go through these in a lot of detail, but I'll just go through some of the highlights. Advanced packaging. So we define things in terms of module. There can be one module, two modules, or four modules. These are the frequencies: 4, 8, 12, 16, 24, 32. For advanced packaging, it's 64 data lines for each module, and these are all single-ended. Other than clock, everything is single-ended. Clock is pseudo-differential. And for the organic, it is 16 data lines. So, if you're running, for example, at 32 gig, and your standard package 16 data lanes, that's the equivalent of a by 16 Gen 5 for a given package. So if you put two of them, then it is like a Gen 6, 3 or 4 of them, it's like a Gen 7 bandwidth. This particular one is 64. If it is advanced package 64 at, let's say, 32 gig, that's the equivalent of a Gen 7 and Gen 8 and Gen 9, right? So it's a lot of bandwidth. And then we have sideband. I'm going to skip over some of these slides, but go directly to the usage model. So at a package level, so there are two broad usage models. The first one is what we have been talking about, that SOC as a package level construct, right? So far SOC has been a chip level construct, but with UCIe, we want to view this as SOC as a package level construct. And different segments have different needs, and that's the reason why we have 2D, 2.5D. You can mix and match. You can have, in this example, you have some processor. In the most advanced process node, accelerators are a mix. You can have 4 processing chiplets, or you can have 2 processing chiplets and have 4 accelerators. You got memory that is connected through this. You got modems, optical, all of these can be connected. So the chiplet types can be, PCIe or CXL based. These would be examples, would be your inference, video, networking, crypto, compression, NIC, memory expansion, or they can be streaming protocols. For example, like scale up, proprietary companies will do their own solutions to build things that are going to do the scale up. For example, these 4 processors will talk to each other and do things using their scale up protocol, right? Same way, some accelerators might deploy scale-up protocol, and then the SerDes kind of connectivity would be through the raw mode. For example, your RF or your modem can be through the raw mode. So those are some of the examples of this mix and match protocols and chiplets using UCIe. This is another example of the scale-up SoC. I want to acknowledge one of my colleagues from AMD whose slide here that I'm using. So for example, this is a CXL switch. And from an economic point of view, it might be reasonable for somebody to just build a 128 switch, because that's a 128 lane switch, because that's the sweet spot. But with UCIe, you can connect 2 of them, form 256 lane switch. and you can connect 4 and do up to 512 lanes. And these protocols most likely are going to be the switch's internal proprietary mechanism, whatever bus they have, they're just going to extend that through the UCIe. Today we construct, if you look at our Sapphire Rapid CPU, it looks very similar to this picture, right? So 1, 2, and 4. So it's a very common construct people are deploying today. This is another example coming from some of my colleagues at ARM and NVIDIA. I want to acknowledge that. So, they envision this is an example case that they have. So compute nodes connected through their CHI protocol using UCIe. In case of an open port, they want the ability to do either CHI or CXL. So that way, if this side does just the CHI, they can just bypass the CXL part and just connect them, or they can just use the CXL as the means of connecting that, right? So mix and match, just like at the board level, we have the same pins do PCIe, CXL, in our case UPI, in somebody else's case something else, but same kind of construct. These are some of the other examples of different usages. So this is a simple PCIe CXL streaming over UCIe. This is the the raw mode kind of thing where you're connecting a SerDes die. So you got your proprietary 5, maybe a 224 gig 5 or 5, whatever is the next generation. You can do that. There is another example I'll talk about, which is that optical, right? Co-packaged optics is another one of the exciting things that we are offering, and offering as in we have provided the UCIe based interface for any off-package connectivity. So you can imagine that you put your co-packaged optics here, put the co-packaged optics on this side, and then now you are going over to a different chassis, potentially on a different rack using optical connectivity. And it looks to you like, this side is almost close enough to this CPU. Of course, other than this package, other than the time of flight here, which is a very reasonable amount for, especially if you are doing these high-speed kind of links. So this was the picture from my 2021 keynote on, some of the future directions. And, at that time I had painted the picture of compute nodes. This load store IO fabric was CXL. You got a pool of memory connected, pool of accelerator, pool of storage, and you wanted to construct these things dynamically, right? Using the depending on the demand, right? So that way, if you need more memory, you come to the pool, get the memory. You want to use it as shared memory for these different compute nodes to talk to each other, or you pick different number of accelerators, you can do that. So the question is, okay, how does UCIe help? So this is where the second usage of UCIe comes in. And if you recall the co-packaged optics that I mentioned, so this is the same picture here. Fundamentally, if we look at the picture here, if you think about, okay, so this is a CPU package. I put a UCIe retimer, which we have defined. And let's say this is the optical connection. So it escapes that particular chassis. I can come over here. This is the same CXL switch die, maybe 256 lane, or I could have put 4 of them and done 512 lane. And on this side, you have pooled shared memory, accelerators, and using the UCIe optical retimer, you are basically connecting that entity over maybe on the same rack or on different racks, right? So all of these compute nodes can connect to this CXL switch and get access to a common pool of resources. So that's what UCIe with its retimers enables us to do. So you can see that not only at the package level, we are able to go outside of the package. We are offering mechanisms for us to escape the package, not just the package, but potentially even the rack. Now let's look into some of the key metrics here, right? So what are the data rates we support? Again, recapping: 4, 8, 12, 16, 24, 32. Standard package is 16, advanced is 64. These are the range of bump pitches. These are the channel reaches. Now let's look into the bandwidth density. So we give the density both in terms of linear, which is per gigabytes. By the way, we mention in gigabytes, not gigabits, because the numbers are fairly big, and square millimeter, right, which is the area. So these are the ranges. So you can go through them. So for example, 188 means that if you run at 4 gig, 32 lanes, if you do the math, it's 188 gigabytes per second per square millimeter. If you run at 32 gig, let's say if you run at 88 gig, then it will be 376 gigabyte per second per square millimeter. 32 gig will be 1350 gigabytes per second per square millimeter. These are all estimated at 45 micron bump pitch. And these numbers, for example, if we go to 25 micron, these numbers will go up by more than about 3.25x, 3.25x, more than 3x. Okay. That's a lot of bandwidth, right? If you look into, something like 1350 gigabytes per second per square millimeter, that's a lot of bandwidth for a very small amount of area. So once the bump pitches really starts to decrease, what my prediction is what will happen is people are going to just dial down the frequency and get much better power efficiency than even what is mentioned here. Because that becomes more important. So power efficiency targets are 0.5, 0.25. Just to contrast, right, the numbers here, on an external interconnect like PCI Express or CXL, these numbers are in the less than 10, or round it up to 10 gigabyte per second per square millimeter. So you're getting, even for the standard package, you're getting an order of magnitude improvement, and in this case, two orders of magnitude improvement, right? 2-3 orders of magnitude improvement. Power efficiency numbers, your mileage varies. For external links, it's between 5 to 10 picojoule per bit. You're getting an order of magnitude improvement here. Now, the other aspect of it is the low power entry and exit, because this is what gives us the bandwidth consumption being proportionate to the power consumption being proportionate to the bandwidth consumption. We have very low entry and exit latency, right? 0.5 nanoseconds for a certain frequency range, and beyond that, it's about a nanosecond. And we get 85% power savings. So let's look at that. So I get 85% power savings, and I can act on it in every 0.5 nanoseconds. So practically every clock cycle, I can decide whether to turn on or turn off the circuits and get the power savings of 85%. Now, how does that contrast with external interconnects? Well, those are in microseconds range, and because we are dealing there with a lot of, those channels are a lot harsher, so the circuits are a lot bigger. As a result, their bandwidth density is a lot lower. But here we are actually being limited by the bump pitch. We are not limited by the circuit area. It's a very simple set of circuits. So really good power saving story, really good power consumption story there. And again, it's going to get better as the time goes on. Latency is less than 2 nanoseconds. Again, an order of magnitude lower. Reliability measured in FIT, which is how many failures we get in a billion hours. It's in the 10 to the power minus 10 range, which is practically zero. So it's a pretty good set of metrics that we have with UCIe. And we believe this is going to sustain us for a long time. Now, the ingredients for a broad interoperable chiplet ecosystem are these 4 sets of things. You have to be in the middle of that to have a thriving chiplet ecosystem. So from a broad market perspective, people are doing chiplets. We know how to do them. After we have announced UCIe, there is a lot of companies have announced their IP, VIP, all of those things are available. People are doing chiplets, so this part is done. And so what we have done with UCIe is address this need, right? So very detailed specs. We are working on the compliance and interoperability, and this is going to lead us to a predictable path of design compliance. And we are happy to be in that happy intersection of these 4 sets that I'm showing here. As a consortium, we have 12 board members. We incorporated in, I believe, June of last year, 120 plus member companies. It's pretty much the who's who, right? And you can go take a look at it. So ecosystem is very excited with the direction. And again, right, we did the same thing with CXL recently, and now this is UCIe about a year into it. Now let's talk about some of the future directions. Where do we go from here? So one of them is, of course, going to be compliance testing. So we are working through, how are we going to do the compliance, right? So, there is this notion of a golden die, and ideally what will happen is that you're going to have, bring your chiplet, we check for it, similar to what we do on PCI Express or CXL. check out the different aspects of it, and we are working on those. Some of the other things are challenges that we have to solve is the set of footprints for the chiplets, how the power delivery and cooling will work, what is the debug and test story. So all of these are going to be important, because the fundamental problem is that some of these chiplets may not have a set of package pins. So how do you test them? How do you debug them? So those are the types of things that will come up as we mature into this area, and we are working on those. Of course, on-package memory is a hot area. We already have the cxl.mem. We are going to look into if there are other possible optimizations possible. The other thing is around reduced bump pitches with advanced packaging. I talked about that. So we are going to get higher bandwidth, means that you can also now reduce the frequency and get more power savings. Then the last but not the least is 3D chiplets, right? So you can imagine a world where these are like small towns and villages where you have got houses that are nearby, and these are like metropolis, right? So you want both will coexist, right? And then the question is that if you have chiplets that you have stacked like this in a 3D fashion, right? You can look into the picture over here. The picture over here where you got the multiple sets of these chiplets connected through UCIe 3D that we're yet to define, of course. But this is the direction, right, of the future that's going, and we have to work on how that works. What is the reliability story? How do we debug? What's the power delivery story? How to do the cooling? Bottom line is there is a lot of interesting challenging problems ahead of us. This is just the beginning of the story with UCIe 1.0, right? We have a long way to go, just like PCIe, CXL. After 20 years, PCIe, we are still going strong. This is just in the starting point, and we will keep on going. So chiplets, and in conclusion, chiplets and die-to-die interface, these are essential to the compute continuum, and standardization will help drive an open chiplet ecosystem. It's the same kind of thing as a slot at a board level. This is your open plug and play slot at the package level, and we just got started. We clearly have a very long way to go, and we are going to solve together the interesting problems as they arise. So probably have time for a couple of questions.
Okay, thank you, Debendra. So if anyone has any questions in the chat, feel free to type them or unmute yourself or raise your hand, and we can ask any questions of Debendra before we conclude. Debendra, I'm not seeing any questions. Cool. Thank you very much.
Well, thank you all very much.